Which of the activities did you find the easiest? Rolling the die or the stopwatch. I got both answers. Which one did you feel like you were the most successful at? Stopwatch. Rolling the die, there's not really like success, right? There's no real goal here. Just what number did you get? Did you find the penny toss to be easy or difficult? Kind of depends, right? Who here got 24 inches or less on the penny toss? Who got 12 inches or less on the penny toss? Ooh, still quite a few of us. Who got 9 inches or less on the penny toss? 6 inches or less? 3 inches or less? 1 inch or less? Awesome. All right, so let's try to match up these activities with their graphs. Activity number 1, the rolling the die. If I were to go around the room and ask everybody, when you rolled the die 3 times, what did you get? What did you get? What did you get? And I made a histogram, like a bar chart, out of everybody's answers. Which of these 3 graphs do you think this would look like? The last one. It's the last one. What's the chance you roll a 1 on the die? 1 out of 6. What's the chance you roll a 2 on the die? 1 out of 6. What's the chance you roll a 3 on the die? 1 out of 6. 4, 5, 6. So the chance of all the different numbers on the die is exactly the same. That's what this is showing me right here. If I were to have my relative frequency over here, each of these would be coming in at 1/6, which would be about, what, like about 16%? So 0.16 about-ish. We call this a uniform distribution. Why do you think we call it uniform instead of symmetric? Is it symmetric or approximately symmetric? Yeah, if I split it down the middle, the left side looks pretty similar to the right side. We call it a uniform distribution, though, because I can have lots of different graphs that have that symmetry down the middle, but I don't have graphs most of the time that look like a rectangle, right? So this is a more descriptive term than symmetric, a uniform distribution. And it looks like right about here is the probability for those. All right, so that's our rolling the die, activity number 1. Activity number 2, tossing the penny towards a target. Which one of these do you think it would look like if we tossed the penny towards the target and graphed all of that data? Let me see your hands again. Who got within 2 feet, 24 inches? If you got 24 inches or less on the penny toss. 12 inches or less on the penny toss. 9 inches or less on the penny toss. Look at how many hands are still up. 6 inches or less on the penny toss. Look at how many hands are still up. 3 inches or less. That's where we kind of lose everybody. Second graph. How would you describe this shape? Skewed to the right, yes. All right, so this last one would have to be activity number 3, the stopwatch, right? How many people got like exactly 5 seconds? You stopped it at 5.00000. Nice. How many people got really, really close to 5 seconds? You were within like 0.02 or 0.03. How many people stop their stopwatch less than 5 seconds? Interesting. How many people stopped theirs at more than 5 seconds? Yes. We've got about the same number that said less than as more than. Most people got pretty close to 5 seconds. That would be this right here. Our range there would be like 4.95 to 5.05. You'd go in that center bar. How would you describe this distribution? See if I can draw that better. What'd you say? Yeah, it is approximately symmetric. In an approximately symmetric distribution, is the mean bigger than the median? Is the mean smaller than the median? Are they about the same? They're about the same in a symmetric distribution. So the mean is going to be really close to the median. Remember when we looked at those summary statistics and I told you guys when you have the summary statistics, so you've got the mean, the standard deviation, the 5-number summary, so you have your median. If you look at the mean and the median values and they're very close together, you have an approximately symmetric distribution. Second graph, the one that goes with activity number 2, the penny toss. The mean and the median. Would the mean be bigger, smaller, or about the same as the median? Bigger. These values over here are going to pull that mean up away from the middle. And what about our uniform distribution? The mean would be bigger, smaller, or about the same? About the same. Again, a uniform distribution is symmetric. And so again, we see this mean and median being really close to the same number. Thank you. These are all examples of something called a density curve. So this is a density curve. This guy's a density curve. This is a density curve. Not the histograms, but kind of the shapes that I drew over those. Density curves, the area of a density curve will always be 1. Or if you want to think in percents, it's always going to add up to 100%. The area under a density curve is always 1. Because the area underneath a density curve is always going to be 1, when I add up all of my relative frequencies, it adds up to 100%. We can use the location in that density curve to figure out about what percentile we're at. I want to look at a really special density curve right now. I've got a dot plot showing the stopwatch times for 100 students. So there are 100 little red dots on here. So this would be the kiddos that got exactly 5 seconds, 5.05, 4.95, and so on. This shape, let's see if I can go over it. Is approximately what? It's approximately symmetric. Have you guys ever seen a bell-shaped curve, kind of like that. So that bell-shaped curve is called a normal curve. And I kind of see that shape here. I did a really poor job drawing over it, but I see that bell-shaped curve happening here. So instead of saying approximately symmetric, I'm going to call this approximately normal. That bell shape. What is the mean of this? Five seconds is our mean. When I know the exact mean from a whole group, we call that mu. This is the symbol for mu. It looks like a fancy M, but the second stick doesn't go all the way down. We use that to represent the mean for a population. And then we have our standard deviation. What's our standard deviation? 0.1. 0.1. We say when this is the standard deviation for a population, the symbol that we use for that is a lowercase sigma. It looks like an O with a tail off the top. So this 5 right here in the center, that's my mean. That's mu. I want to figure out what percent of these values are within one standard deviation of the mean. So I'm going to add and subtract the standard deviation to the mean so that I can go out on either side, both below by one standard deviation and above by one standard deviation. How far above would I need to go to catch one standard deviation? What was our standard deviation again? 0.1. So the mean 5 plus 0.1. This is my mean plus 1 standard deviation. What about going on the other side of the mean? Where would I go? What would be 1 standard deviation away on the other side? 4.9. This is my mean minus 1 standard deviation. So I want you to look between those. I want you to figure out how many dots there are in between those 2 green fences. Did anybody get a count of all the dots? 68. Out of how many dots did I say there were? 100. So my percent, I'm going to do 68 divided by 100, which comes out to be what percent? 68%. I'd get 0.68, which is 68%. So 68% of all of those dots fall between one standard deviation on either side of that mean. So most people got that close, right? More than half of them. What percent of the values are within 2 standard deviations of the mean? Here's my mean at 5. Where would I go if I was doing 2 standard deviations above the mean? 5.2. So here's my mean. Hold on, let me move this down just a little bit. This is my mean plus 2 standard deviations. What about below the mean? 4.8. This would be my mean minus 2 standard deviations. So now I'm going to make fences here and here. We already know that between the 2 green fences is 68, so you need to add up how many more we're adding on top of that. Figure out how many dots total in between these 2 purple fences. Or you could look at how many dots were left out and do what? Subtract it from 100. How many dots are there? 95. Out of 100. So what's my percent? 95%. What percent of the values are within 3 standard deviations of the mean? Does my graph even go out to 3 standard deviations? Where would 3 standard deviations be over here on the right-hand side? 5.3. Let's go ahead and add that. 5.3. This is my mean plus 3 standard deviations. And what about on the other side? 4.7, which would be about here. That is my mean minus 3 standard deviations. How many dots fall in between those two? 100. All of them. 100 out of 100. That would be 1, or 100%. This right here is called the empirical rule, which we're not exactly precise. There's one little alteration that we have to make to this. EMPIRICAL. The empirical rule, sometimes called the 68, 95, 99.7 rule. 68, 95, 99.7 rule. %68 of our data, when we are approximately normal, we have this bell-shaped curve. 68% of all the data will fall between 1 standard deviation of the mean, both above and below. 95% of all of the data will fall within 2 standard deviations of the mean on either side. And 99.7% will fall within 3 standard deviations. So close to all of it. Describing the shape of this distribution, we are approximately normal. When we have an approximately normal distribution like this, I'm going to draw a bell-shaped curve down here. Sorry, my art's not super great. When we see an approximately normal distribution, we label it with a big capital N to mean normal. And then we have parentheses, and we're going to give some information about this distribution. We're going to give the mean first. And then we're going to give the standard deviation. So for this graph up here, I would label this with a capital N. And then I would put the mean of 5 and the standard deviation of 0.1. And now I will tell you that on the AP Stats exam, when you go and do something like this, they want to make sure that you know what those two numbers mean. So we go in and we label them with what they are. This first one is my mean. The second one is my standard deviation. So above or below those numbers, we're going to label them so that they know that you know what those numbers are and where they're coming from. So we're going to practice doing that every time we have a normal distribution. We're going to have a capital N, and then inside parentheses, we'll put our mean first and we'll label it. We'll put our standard deviation and then we'll label it. Let's go ahead and flip it over on the back. My density curves. The total area under a density curve is 1. The area from a certain location in that density curve, from that point over to the left, that gives me my proportion of values, or my percentile. Gives me my percentile. And then in my distributions here, if we have a skewed right distribution, the mean is going to be bigger than the median. If we have a symmetric distribution, the mean is going to be approximately the same as the median, and skewed left, the mean is going to be smaller than the median. Here's our empirical rule sketched out for us. Within 1 standard deviation of the mean is 68% of all of my data. So this right here would be 68% of the area under that curve. Within 2 standard deviations, so this right here, all the way over to here. Do you see how I've colored in most of that curve? That's 95% of all of the area under that curve. I caught almost all of it. Going out to 3 standard deviations, I need a bigger pen for this. If I shade in all of that space, I've only left out this little tail over here and this little tail over here. That's 99.7% of all of the area under that curve. I want you guys to do number 1, part A. We'll do the rest of it tomorrow, but I want you to do number 1, part A, and we will check that here with mine in just a moment. We're going to take about 2-ish minutes for number 1, part A. So I want you to sketch the curve in. I want you to draw in the mean and where those standard deviations fall on either side. I want you to take it out to 3 standard deviations on either side. And then I want you to label the mean. What is that actual value? Put a number there. 1 standard deviation above would be what number? 2 standard deviations above would be what number? 3 standard deviations above would be what number? And then I want you to do the same thing for standard deviations that are falling below the mean. What number should go right in the center? 44. 1 standard deviation above would be what? 48. 2 standard deviations above? 52. 3 standard deviations above? 56. So you should have 44, 48, 52, and 56 labeled. What about 1 standard deviation below the mean? 40. 2 standard deviations below the mean? 36. And 3 standard deviations below the mean? 32. You should label this distribution, big capital N, because it's a normal curve. Then we put our mean and we label it, standard deviation, and we label it. We're going to finish up this Check Your Understanding tomorrow. The homework that you guys picked up on your way in the door is due on Friday, but we haven't really gotten through very much of that yet. What I want you to do tonight, don't work on the paper homework. Do some reading tonight, pages 109 to 136. 109 to 136 is what I would like for you guys to do for homework.